right, so I want to ask the question, is the converse true? And so when I say converse, I'm referring to the conditional statement, if f is differentiable at a point, then f is continuous there. The converse of that is if f is continuous, then f is differentiable. And we want to figure out, is that true? And so I wanted to look at a specific example with you, the absolute value function. So it's easy to see visually that this function is continuous at 0 because there's no holes or jumps or anything. It's all good. But now let's ask ourselves about the derivative. Hopefully you can see that the derivative exists anywhere away from this point at 0, right? The slope of the tangent line to a line is the line. So for example, the rate of change here is the rate of change of this line itself. So everything is good as far as the derivative goes, except at 0. And so let's imagine now, or let's not imagine, let's compute g prime of 0. This is the limit as h goes to 0 of g of 0 plus h, which is the absolute value of 0 plus h minus the absolute value of 0 all over h. And this is just the limit as h goes to 0 of the absolute value of h over h. And now this limit does not exist. We actually did this back in chapter 1. I'll just mention why. The limit as h goes to 0 from the right of absolute value of h over h. This guy is just 1, but the limit as h goes to 0 from the left of absolute value of h over h, this guy is negative 1. And so that limit doesn't exist. And so what this means is here's a function that is continuous at 0, but is not differentiable there. And so let's make sure that we answer our question. The answer is no. So if you're differentiable at a point, then you are continuous at that point, but the converse need not be true. And so I want to work through just a couple of examples of some ways that a function can fail to be differentiable. This is not necessarily an exhaustive list. It turns out there's a lot of nuances to this idea of being differentiable, but here's a couple. So one is that anytime you see a cusp, then you know that, anytime you see a cusp, you know that the function is not differentiable at any sort of sharp point like that. And actually, we can sort of see why a little bit. Let's zoom in. And I want you to imagine with me tangent lines at this point. And the big takeaway is there's not just one tangent line. There's a tangent line, there's a tangent line, there's a tangent line, there's a tangent line. There's actually infinitely many tangent lines. And so the problem is there's sort of too many tangent lines. There's not one unique tangent line that the function looks like the closer you zoom in. But anytime you see a graph, if there's like a sharp cusp point, a corner of some sense, then it's not, the function's not going to be differentiable, though it might be continuous there. Here's an example of a function that you know is not differentiable at these points simply because it's not continuous there. So we'll just say that anytime you have a discontinuity, discontinuity, then you know that you're not differentiable there. And finally, it's possible to have a vertical tangent. And my graph here by hand is a little bit maybe misleading, but there's actually a vertical tangent line at 0. And so, of course, the derivative does not exist at 0 as well. So these are just some ways to keep track of in your mind as we go along. So I want to make two quick comments, and then we're going to switch to Mathematica. So first off, this is really important. And so if the derivative exists at a point, then zooming in on the graph of the function far enough at that point is going to look like a line. It's going to look like a line. And in fact, it's going to look like its tangent line. I'm going to erase like it's, let's say it like this, like its tangent line. All right, and so we'll actually look at that in Mathematica in just a moment. The other thing that I want to mention is this crazy function called the Weir-Strauss function. And so it turns out that in the 1870s, a mathematician named Carl Weir-Strauss questioned the prevalent belief that every continuous function is differentiable except for a couple of points. And all the examples that we did, that's what's happening here. There's a few points where it's sort of not differentiable, but most places being continuous mostly is differentiable. And so he stunned the world with an example of a function that is continuous everywhere but differentiable nowhere. And so I'm going to switch to Mathematica, and I want to show you zooming in on a function looking like its tangent line, number one, and then number two, an example of a function that is continuous everywhere and differentiable nowhere. So let's switch the screen. All right, let me drag my Mathematica notebook over. Here we go. And I've gone ahead and just made up a function in blue, and I've got the tangent line to this function at 2 plotted, and I just want to zoom in on the function near 2. And so right now I'm graphing from minus 1.1 to 3.3. So for example, let's zoom the graph in. We'll say from 1.5 to 2.5, and we zoom in. And so you can still see a difference between the function and its tangent line. But now let's zoom into like 1.8 to 2.2. 1.8, 2.2. Still see a difference, but they're starting to look more and more similar. Now we can go, 1.9 to 2.1, and you can still see a difference. Now let's go like 1.95 to 2.05, and getting closer and closer. We're zooming in deeper and deeper. They look almost the same, except for the very ends here. And now we can go 1.99 and then 2.01. And at this point, I can just barely see a little blue here and here. And if we add another zoom, you can't even tell them apart. So at this point, the tangent line and the function look identical. I'm actually going to pull the tangent line off now. So you're seeing it in yellow. I'm going to get rid of it and then replot just the function. And it's the same, right? That's what the function looks like if you zoom in close enough. And so the point is, when you think about a function being differentiable or not, I want you to realize that differentiable in some sense means if you zoom in on the function far enough, it's going to look like a line. And so when you compute the derivative or dy dx, you're literally computing the slope of the line that the function looks like at that point. Okay, very good. So let's get rid of this one. Bye-bye. And we're going to pull over this other notebook right here. And so this is a computer sort of mock-up of the Weir-Strauss function. You actually can't really graph it, but we'll do our best. And so we're going to zoom out. And you can kind of see that it's a really weird function. It's jagged. So we're zooming in somewhere. Let's zoom in right here, maybe around 1. And now we're going to zoom in a little bit. And every time we zoom in, for a moment you can see Mathematica trying to render it, and then it gets fuzzy again. Do you see? And then we zoom in some more, and it looks like, oh, that's a regular function. It's continuous. But when you let go, it's fuzzy again. And basically, it doesn't matter how far you zoom in on this function, it's never going to look like a line. It's always going to look kind of fuzzy and jagged. It's kind of like a fractal. You may have heard of those. And so you can just keep zooming and zooming and zooming all you want, and you're never going to get an actual curve that's smooth and looks like a line. And so always these points are somehow all connected. It's pretty incredible. So it's continuous. You never pick your pencil up, but every single point, there's no derivative. So this is the Weir-Strauss function, or at least a computer mock-up of one. All right, well, let's go on to the next video and see what's next.